Hello everyone, this is Sarbajit Dutta and welcome back to Educathea. So in our last lecture, we have seen what the energy distribution of spectral radiation of black bodies looks like. Now the thing is, we have missed out on a term, the term for average energy. And in this video, we plan to give you a glimpse of what the calculation of average energy might look like. So Billy, would you lend me the blackboard please? Thank you, Billy. So in our last video, we have seen the expression for E nu d nu, which looked something like this: C by 4 into 8 pi mu square by C cube epsilon bar into d nu. And now our question is to find out the value of epsilon bar. What is epsilon bar equal to? And if we can know this, if we get the expression for epsilon bar, then we will get the expression for this entire E nu d nu, which will give us the final answer. So our aim is to find out epsilon bar. In fact, it was Gustav Kirchhoff in 1860 who challenged the physics community with this problem. In fact, there are three candidates who gave some expression for this epsilon bar. So candidates for energy distribution. Candidates for energy distribution. Who are they? Number one, in 1866, it was Wien who gave his famous Wien's radiation law, which gave us an initial idea about what epsilon bar might look like. So this was the very first idea which someone gave about epsilon bar. Now, this had some errors in it, so it was not recognized after some time. Then it was in 1900, Lord Rayleigh gave his expression for epsilon bar. But again, this had certain flaws in it. In the same year, that is 1900, after some time, it was Max Planck who gave his Planck's law or Planck's radiation law, which exactly explained how E nu d nu should look like. So this was the correct expression for E nu d nu. 100 marks, absolutely fine. But then again later on in 1905, it was Sir James Jeans who gave another expression which looked very similar to Rayleigh with just a few corrections here and there. So both of these expressions together, they are known as the Rayleigh Jeans Law. The Rayleigh Jeans Law. And just as I mentioned, this was not the right exact expression for E nu d nu. This had certain minor problems in it. But then the question is, then why did people accept Jeans' law at all? Because we already had Planck's law in 1900s. So why did after 5 years people accept a wrong law? Well, this brings us to a very important fact in science. It appears that there are prejudices in science too, especially in science communication. In fact, very ironically, Jeans published his reports in the same magazine in which Planck had published his reports 5 years earlier. It was the same philosophy magazine in which both of these reports were published. It appears that maybe Jeans knew the editor of philosophy magazine who helped him to publish his reports, even after Planck had originally given the correct expression. But nevertheless, this is what the picture looks like. And now let us study each of these laws individually. We will start with Wien's radiation law, we will study the Rayleigh Jeans law, and then in our upcoming lecture, we'll learn about Planck's law in totality. Right, so let's talk about Wien's radiation law. So Wien's radiation law. So we are all aware of the black body radiation curve that we have been talking about time and again. So it looks something like this. something like this, yeah, where the x-axis is calibrated in frequency nu and the y-axis is a function of frequency. What is this function of frequency? It is E nu, that is the energy emitted within the frequency range nu to nu plus d nu, which is again given by something like this, which we have discussed. Now our job is to find the value of epsilon bar so that we can get an expression which fits this curve. Now if you remember correctly, then the graph for Maxwell's Boltzmann distribution looks very similar, isn't it? So I'll try to draw the curve for the Maxwell-Boltzmann distribution. It also looks something like this, where the x-axis is calibrated in velocity and the y-axis is a function of velocity. So basically, what is this velocity? This velocity is the velocity of gas molecules. So let's say if you have a container full of gas molecules, each molecule is moving with a velocity v, then this function f of v tells us how many fraction of the total number of molecules is moving with a velocity between the range v to v plus dv. So fv is basically given by m by 2 pi kt to the power 3 by 2 into e to the power minus e by kt. Now what is this? E here is the energy of the gas molecules and k is the Boltzmann constant, right? So we can see a clear resemblance between these two curves. However, the thing is, here in Maxwell's Boltzmann distribution, we have an exponential quantity which lacks in the black body radiation curve. So maybe this epsilon bar is somewhere related to this exponential term. Maybe that's the reason why we get a curve like this. It's very much possible. And you know what this exponential term serves as? This exponential term serves as the probability of getting a gas molecule of the energy E. So that is what this exponential term serves as. So if we carry forward with this assumption, then what we can do is we can write epsilon is equal to some constant alpha into e to the power minus e by kt, where E is the energy of the atomic oscillators which vibrate and give out black body radiations. If you remember, we had considered a box like this with a small opening, and within this box there were atomic oscillators which vibrated. So this E stands for the energy of these atomic oscillators. But now this epsilon bar, this is an energy, right? This has dimensions of energy, and the exponential term is dimensionless. So alpha should have dimensions of energy. Now let's go back to Maxwell-Boltzmann distribution again. The energy here, if you remember the formula again, the energy here was a function of velocity, because the energy here is technically kinetic energy. So energy is a function of velocity here. And we can see that the curve has velocity in the x-axis. Here in the x-axis we have frequency. So maybe this energy over here is a function of frequency mu, maybe. So let's try. So if the energy over here is a function of mu, then epsilon bar will be something like this, e to the power some constant a into mu divided by kt, so that a nu and kt have the same dimensions, which is the dimension of energy. Because A nu by kt, this should be a pure number, a dimensionless number. Only then you can apply exponentials to it. If this is the case, then we know that the dimension of energy has a dimension which is a product of some constant into frequency. And alpha also has the dimension of energy. Then maybe alpha is also of the form some other constant, maybe b into nu. So epsilon bar is basically some constant b into nu into exponential of some other constant a nu divided by kt. Now if we put this in our formula for E nu d nu, if I add d nu, then it becomes the energy distribution. Then this becomes c by 4 into 8 pi mu square by c cube into b nu e to the power minus a nu by kt into d nu. And to our surprise, this expression fits this above curve perfectly. Now, when Wien calculated this, he was not really sure about what these constants a and b are. Later on, when Planck gave his own calculation, then it was proven to the physics community that a and b, they are basically the same constant called the Planck's constant h. The Planck's constant. So now the new expression becomes E nu d nu equal to c by 4 into 8 pi mu square divided by c cube into h nu into e to the power minus h nu by kt into d nu. And this is the Wien's radiation law given by Wilhelm Wien in the 1860s to the 1890s. So this is a very popular formula and it fits this curve beautifully, this one. But then again, it has some problem in it. Let's look at the problem now. So if you plot the graph for this distribution, it looks something like this. It looks something like this. But then again, this is f nu and this is nu. F nu is nothing but E nu, right? But then again, if you plot the experimental values, then you get a curve like this. So till this point, I mean in this region, the curve matches exactly, but towards the left hand side, the red dotted curve shows what the experimental data is, right? So with increasing mu, the curve fits beautifully, but when you decrease nu, when the frequency goes on decreasing in the IR region, then this Wien's radiation law fails to describe the correct nature of black body radiation. So this fails in the IR region. IR region. This was in fact experimentally proven too. Friedrich Paschen in the year 1897 supported that in the increasing frequency region, the curve fits beautifully. But then again, Otto Lummer and Ernst Pringsheim in around 1900s proved that the curve fails to fit in the IR region. Wilhelm Wien got the Nobel Prize for this in the year 1911 in physics, but nevertheless, it still doesn't give us the complete picture. This was an excellent attempt by Wilhelm Wien, but the picture is still not complete. And this brings us to the second approach by Rayleigh and Jeans. Right, so let's talk about Rayleigh Jeans Law. Rayleigh Jeans Law. So we know how we modeled black bodies. We considered a small box like this, which had atomic oscillators which vibrated within the walls of this cavity, and then they gave out electromagnetic radiation, which is basically what black body radiation is. Now, if you carefully examine this picture, these atomic oscillators have 2 degrees of freedom. They can either vibrate up and down, or they can vibrate left and right. So there are 2 degrees of freedom, which these atomic oscillators are entitled to. Now we are going to use the equipartition theorem from thermal physics, which tells us that for every degree of freedom, you have half kT of energy associated with it. So the total energy here is the average energy, of course. The total average energy due to 2 degrees of freedom will be half kT plus half kT, because for each degree of freedom you have half kT. This is the theorem of equipartition. So for 2 degrees of freedom you have half kT plus half kT, which is nothing but kT. Now if you put this in the original picture, then E nu d nu becomes c by 4 into 8 pi nu square by c cube into kT into d nu. Now this is called Rayleigh Jeans Law because Rayleigh originally gave this calculation, but then it was Jean who fixed these constants in the calculation. Rayleigh did some mistakes in getting these constants, but then Jean again fixed them. So it is called Rayleigh Jeans Law in totality. So the Rayleigh Jeans Law looks like this, whatever I have written here. Now let's try to draw what this E nu d nu expression looks like. So it looks something like this. This is E nu and this is nu. So this is what the curve looks like. But then again, we know what the original experimental curves looks like. It looks something like this. So here in the lower frequency range, in the IR range, the curve fits beautifully. But in the higher frequency range, in the UV range, the curve suffers a catastrophe. In fact, it says that if you keep on increasing frequency, energy will keep on increasing infinitely, indefinitely. Now this is a catastrophe in classical physics because such an idea is absolutely weird and absurd. Energy cannot keep on increasing if you increase frequency, because then at some point these atomic oscillators will become so energetic that high radiations will come out, and I mean weird and absurd things will happen. That doesn't happen. So this explanation is totally weird and absurd. This is why Paul Ehrenfest called this the ultraviolet catastrophe. The ultraviolet catastrophe, because this fails in the UV region and the failure itself is of catastrophic kind. So yet again we find a problem with Rayleigh Jeans Law. The previous law, the Wien's law, fitted the curve in the higher frequency range, and Rayleigh Jeans Law fitted the curve in the lower frequency range, but none of them fitted the curve in totality. So Wien's law failed in the IR region, and Rayleigh Jeans Law failed in the UV region. These are the failures which they encountered. So we still don't have a law which can explain the curve for black bodies completely. In our upcoming lecture, we will see, in fact, there does exist a law which beautifully satisfies the experimental curve. It is the Planck's radiation law, which gave birth to what we call as quantum mechanics.
Thank you so much for watching this video. Do not forget to like, comment, and share this video with your friends as much as possible. And also don't forget to subscribe to the channel, because that would serve as a motivation for me to come up with more such beautiful videos. Also, kindly press the bell icon over there so that you get a notification each time I upload a new video. Don't forget to check the description box down there for more updates, and have fun and enjoy science.